Dear colleagues, dear friends, so let me present a result which was obtained in our quantum team at the Department for Theoretical Physics. Subject is study of spin system on quantum computers. In fact, I plan to give some short review of our results. Also old result, and but I will be focused on a new one, new results. Okay. So here what I plan to consider. So introduction of our algorithm for study and calculation of spin system and quantum computers. Let me omit, it is written, you can see it, okay. And introduction. So here I presented not all, but main result, which I think is interesting for you, what we get for spin system on quantum computer. So first of all, I would like to say about using quantum computer for study entanglement of quantum state, pure quantum state. So it is possible to find entanglement between spin and some another spins using quantum computer. It is one of the studies. So next, it is possible to study graph properties. So when you have a classical graph, and for instance, you want to find number of triangles in this graph or squares, from classical point of view, it is not so simple problem. So we have some idea, some algorithm of calculation using quantum properties, triangles and squares in a classical graph. So, and as for me, very interesting result is result concerning energy levels of system. Now we recognize that this method which we propose can be used as supersymmetric method. So now we find some some background of symmetry of this method. This symmetry is just supersymmetry. Now, finally, I would like to find you possibility of calculation partition function. For instance, Eisen model quantum computer is not so simple problem. I explain in detail later. Finally, we can have a possibility also find the ground state of Eisen model. It is very important problem from combinatorial optimization point of view. So from classical, for classical calculation, combinatorial optimization problem is not so simple. So quantum computer gives some advantage for solving this problem. So let us continue. So result which I consider just now, it is obtained with together with Christina Gnatenko and Laba Hanna from Polytechnic University. Christina is not here. So publish it here, and let me explain. Let me explain in more detail. No, it's not good. Okay. So what is the idea for calculation energy levels on quantum computers? So when you consider evolution of quantum system, it is not, in fact, very problem to create evolution of, for instance, Eisen model on quantum computer. You have quantum gates. Using quantum gates, you can simulate Eisen model, evolution of Eisen model quantum computer or some another quantum system. But how we can use this evolution to get energy levels? First of all, let us consider some operator, and let us calculate mean value with this operator. You find that result depends on difference between energy levels. So you have harmonic functions as functions of temperature, where we have just, and this frequency is just difference between energy levels. So mean value of arbitrary operators contains different distance between different energy levels. So when we calculate such value on quantum computer, you can find, of course, this distance using Fourier transformation, but it is not very good idea because
what kind of distance?
Distance between energy levels, I mean. This
Difference.
Difference. Okay, sorry.
The distance.
Yes, okay. Understand. Sorry. So, okay. And here, when you use Fourier transformation, so you find that you have a sharp peak at this point, and using this sharp peak, you can find this transition frequencies, frequencies of transition between different energy levels. But it is not very interesting because we want to have energy level, not distance, not difference between energy levels. So how to find energy levels? And here we have idea which give us possibility to find energy levels. Idea is the following. Let us look at the mean value of operator which anti-commutes with Hamiltonian. It's just main idea of this method. When you consider mean value of operator which anti-commutes with Hamiltonian, what we get for mean value? It's very simple result from you find that this mean value depends accurately on the energy levels or double energy levels. So then Fourier transformation gives you sharp peaks at points related to the energy level, so you can find the energy level, no problem. But you must find operator which anti-commutes with Hamiltonian. So it is not always possible, but nevertheless, let us consider a very simple example. Spin chain with three spins, Eisen model.
Not 5.
Three.
No, but for Christina, 5 is important for music.
Yeah.
So
here only three, sorry.
Only 3, yes.
But only 6, also 6 will be, okay. Okay, only three. Okay. In this case, you can easily find that sigma 1x here operator which anti-commutes with this Hamiltonian. It is very simple because x component anti-commutes with z here and with z here. So it's not very problem to find operator here which anti-commutes with total Hamiltonian. Here is presented algorithm for calculation of evolutions. It corresponds to interaction between 0 and 1 spin. It is interaction between 1 and second spin. Here is measurement of mean value of sigma 1x. Okay, what we get, and here is also very important because initial state is very important for this evolution. Here is Hadamard operator, which creates state which contains all possibilities for this state. It is sum of all possibilities for energy levels. Okay, what is the result? Here is result theoretical. It is solid line, and these crosses, it is just experiment on real quantum computer. Not so good, but nevertheless, let us look at the Fourier transformation. Of course, here we have some discrete Fourier transformation related to these crosses. Let me omit details, but what result? It's absolutely exactly corresponds to energy levels. When you find from these peaks energy levels, it corresponds to perfectly to energy levels of this model, which you can find theoretically without any problem. So quantum computer in this case gives very, very nice result. It is real quantum computer, noisy quantum computer for 3 qubit. Okay, more complicated system. And here I would like to present result where we consider these 6 spins. this one. And what is operator anti-commuting in this case is written here. Okay, more complicated more protocol and result. I like this result. In fact, it's very bad, but here is theoretical line, solid line, and here you find results from blue crosses from a quantum computer. It looks very bad, but Fourier transformation gives good result for energy levels. So it is in fact theoretical result, but you can find also some relations. Look here, this peaks absolutely corresponds to this one. Not so good, but nevertheless, starting from such result, we obtain not bad result for energy level. And this peaks very corresponds very nice for theoretical result. Okay, it is related with SUSY algebra. It's very interesting. Let me omit this relation, symmetry with calculation. Okay, and more complicated system. Here I present the Hamiltonian, for which it is impossible to find operator which anticommutes with this Hamiltonian. You can find energy levels, and you find that structure of energy levels does not correspond to supersymmetric properties. And so it is impossible for such Hamiltonian to find operator which anticommute with this one. But idea is the following. Here we use some ancilla qubits or additional qubits sigma 0, which we multiply with Hamiltonian H, so we call it a total Hamiltonian. And for this total Hamiltonian operator which anticommutes, it's very simple, sigma 0x, for instance. So then we can apply the same method, but only for ancilla qubit. And the result for this Hamiltonian is here. This peaks corresponds to energy levels for this model. Okay. So this method, I would like to say, this method, as you see, is noisy resistance. So we have noisy quantum computers, but even for 6 qubits, we obtain not bad result for energy, very good results in this case for energy levels. What about application of this method? So at the discussion, panel discussion, it was questioned, we have, for instance, only 5 quantum bits. What we can do with such computer? There is some interesting possibility to use such quantum computer to simulating a real quantum system. And I would like to present here some possibility. There is very nice phenomena. It is single spin tunneling. It means that when you have one spin, and you have a spin in position up, as a result of tunneling, you can obtain spin in position down. So it is experimentally observable phenomena. Not so simple for observation at the experiment, but we can simulate this system absolutely directly on quantum computer. So Hamiltonian, which was used by experimentalists, is here. It is spin 1. It is possible to simulate such system on quantum computer. Here, let me omit calculation. Here is energy level of this system. It's not problem to calculate. And what about simulation of quantum computer? Spin 1 can be simulated using 2 spin 1/2. And so, as a result of such simulation, we obtain Heisenberg model for 2 spins, and such Hamiltonian can be without a problem simulated on real quantum computer. Then we can apply our method for calculation energy level. This here is protocol. I omit details. Once more, here we have Hadamard operator for preparing initial state. Very important moment for this method also. So here is energy level which we get. Once more, we obtain very good result. So we can observe phenomena of spin tunneling, spin 1 tunneling using quantum computer. So even such small quantum computer with 5 quantum bits give a possibility to simulate a real quantum system which corresponds to just tunneling, single spin tunneling. Okay. So it's one more result, and moreover, we can directly find this tunneling. Let us consider a mean value of that component. So when we start from spin up, as a result of tunneling, we must obtain spin down and so on. So what we get on the quantum computer, here is theoretical result, so solid line, and here is real experiment on quantum computer. You find very good fitting results from quantum computer and theoretical result. So at the initial state, we have spin up. Then as a result of tunneling here, you find spin down and so on. So we can directly find such tunneling. We can observe this tunneling on quantum computer. Okay. Here I would like to present you very shortly calculation of partition function. So problem with calculation of partition function is the following. On the quantum computer, you can simulate unitary operators, but operators which we have here, it is not unitary operator. It is problem how to simulate this Boltzmann factor on quantum computer. So we must find some relation between Boltzmann factor and this unitary operator, and it is possible. It is possible, and I omit details and show result only for very simple model. It's two spin system, now more simple, only 2, not 3. But here we use ancilla qubit, and idea is the following: using this effective Hamiltonian, and when we consider trace over ancilla qubit of this unitary operator, we obtain Boltzmann factor. So we obtain mixed state, which corresponds just exactly to Boltzmann factor. What is the result? Result is here. A solid line is partition function, and these crosses, it is result from quantum computers. 5 is related with temperature, inverse temperature. Very good result. But more interesting that possibility to find partition function give us possibility also to find ground state. How to find ground state? The idea is well known. When we consider action of this Boltzmann factor on the initial state, which can be presented as linear combination over all eigenstate of Hamiltonian, you find that in the limit beta tend to infinity, survives only ground state survives. So by such action, you can find ground state, and what result? Result is here. Explanation you can find here. No, here it is here. But from this histogram, you can absolutely exactly find the ground state for this system. And ground state just corresponds to interaction with opposite direction of spin. Okay, and here finally I would like to present result. As for me, it's very interesting result because this result show progress of quantum computers in time. Result is obtained together with Andrei Kuzmak, is present here. Maybe 1.5 year ago, result for correlation function spin 1 and spin 1/2 on quantum computer is presented here. Very bad result. Solid line, it is correlation function for theoretical result, and here is just corresponds to result from quantum computer. You found 5 minutes, okay. You find that it is solid straight line. Looks so very bad result, and of course that referee asked why such bad result. Proposition was the following. Proposition from a referee, we was forced to recalculate this result using a new quantum computer, maybe 1 year new quantum computer. So what is result? Result is presented here. Is very good result. So 1 year before we have such a result, and after 1 year we obtain very nice result, and this result shows the progress of quantum computer. So it is experimental progress of quantum computer. Conclusion is here. So study evolution of spin system of quantum computer. We can calculate many properties of this computer: energy levels, partition function, ground state, many what you want. So, and with this, I would like to thank you. Thank you very much.
Thank you very much. Thank you for a nice talk and finishing on time, in fact, ahead of time. So we can open discussion. Any questions? Yes, please.
Yeah, thank you very much for your talk. And just a small question. Do you have a theoretical proof for the fact that that's maximum for noisy quantum computer are the same as maximum for ideal quantum computer?
Very interesting question, and it is question we always also from referees. So
it was not me.
Yes, I understand. So we can find using quantum computer. We also have error bars. So on the noisy quantum computers, we also have error bars, and on this final slide, you can find these error bars. So you have this result, and also error bars related with noise. With noise, and you can find if your theoretical result is in this border.
Okay, but if you consider at the very beginning that your quantum computer is noisy,
yeah,
can you predict classically this noisy picture that you demonstrated? For example, you know, so just suppose you know all characteristic or noise characteristic of this computer.
I just say about this. Yeah, we know characteristic of quantum computers from the side. We know error bars from the side. We know errors related with readout. We know now we know the errors related with gates. So and
so
then
you
can
reproduce
yes, and then we can calculate real errors which you have on this quantum computer. So
okay, thank you.
Good. Yes, there is a question over there, please.
What you can say about the possibility of calculation using SUSY methods, system with higher spin, for example, 3/2 or 5/2?
Oh, yes, nice question. Interesting. We have just with Kuzmak paper published where we propose the method for simulation on quantum computers spin, arbitrary spin. Of course, it is problem only with errors. When you have a very large spin, it is more difficult algorithm for simulation, and as a result, you have more errors. But it is, in principle, it is possible to consider arbitrary spin.
I ask you this question because I am experimental theater and we have system with higher spin and need for calculation the spin levels as a function of external field and crystalline fields and all this interaction.
Yes, yes, very interesting because we are interested in the situation when we can simulate a real system on quantum computer. So it will be interesting to consider a real system with high spin and try to simulate on quantum computer to find some interesting properties and to compare with the real experiment in the nature. So thank you.
Okay, thank you very
Thank
much.
you. Well, a question by Grzegorz.
So very interesting talk. So I'd like to ask a question because I understand that going into quantum with this simulation makes sense because, well, it's going to scale much better than classical computers for this part. So there was a question about for which spin systems can you do that? So for which spin systems it would be feasible to do on classical computers yet? Because as far as I understand, for this case, probably you could do classical, right? But how many qubits do you say that would be necessary for this particular task to outperform classical computers?
How many classical bits you need?
No, I would say from the opposite direction. How big would you need your quantum device to be so that it outperforms classical devices for this particular task?
Okay, so you have some classical system.
No. I mean, you want to calculate with evolution of this spin.
Yes, this quantum system.
But suppose with the higher spin, right?
Yes.
And at some point, as you increase the spin, it's not going to be doable on classical computers.
How many need?
And my question is, how many qubits would you require for this particular task? So from the quantum perspective.
Okay, when you have a spin 1, you need 2 qubits. When you spin 3/2, you must have 3 qubits, so on.
So it scales linearly, right?
When you have a quantum spin 2, you need 4 quantum bits because 1 quantum bit spin 1/2.
Okay, so it scales linearly on a quantum computer and exponentially on a classical one.
Yes.
Right.
But when you consider interaction, it is more complicated because, for instance, you have spin in power squared spin. So then you have interaction between many quantum bits. So not only number, but only interaction is we have more in different interaction here.
Okay,
So
thank
more
you.
complicated.
Yeah. Perhaps the last simple question. I'm sorry I interrupted you during your talk. I was very much interested as you used the word distance, but in your case it was just the energy difference. But
yes.
yeah, but are you interested to find a distance between real distance, mathematically speaking, a distance which has such a properties that for eigenstates of some Hamiltonian, this distance is equal to the difference of energies? Would it help you?
Distance between what?
Between 2 states. You have 2 states.
Distance
State, second state.
states.
Yes.
As I know that such distance between quantum states, geometric distance.
Sorry, induced by a Hamiltonian. So for a given Hamiltonian, you have such a distance that the distance between 2 states, eigenstates, is just the difference, like energy difference you are using.
Yes, but when you have eigenstates which corresponds to different eigenstates, this eigenstate is orthogonal.
Yes.
But when you have orthogonal states, for instance, when you could consider Fubini study,
Yes, they are
so
maximal.
the maximal, yeah.
Okay, so let's discuss it later. Now I think it's good time to thank the speaker again.